Hello. In this video, I'll introduce to you the ideas of integration of a function of two variables. So here are some of the goals I've set for you for after you watch this video and read the corresponding section in the textbook. But I'd like to start by considering how we think about definite integrals in a single variable case, so in your Calc 2 class. So what do we think of when we see this definite integral symbol, the integral of f from a to b with respect to x? Well, the first thing that comes to mind might be the area under the graph, under the curve y equals f of x. Well, it's more correct to say the signed area because the area is allowed to be negative if it's under the x-axis. The second relates for us a rate of change with a total change. This is the fundamental theorem of calculus. So if this rate of change is, say, a velocity, then the integral gives us the total change. That's the change in position. Or if the rate of change we think of as a density, then the net change would be a mass. And the last one I'll just put on here is relating the integral to the average of a function. So how do we set out to do this in our integral calculus class? We use the idea of Riemann sums. So remember, we take our interval from a to b and we slice it up and we subdivide it. In each of those regions we pick a point, and we have different rules for how we might pick that point. It doesn't really matter, but we let the point determine the height of that particular bar, that block. The width of each block, delta x, depends on how many subintervals we have. And then we add up the area of those, that is the length of the base times the height. And that sum gives us an estimate for the integral. To get a better estimate, we slice it up into more bars, and we take the limit as the number of subintervals goes to infinity, or as the width of each one goes to 0. We call that value the definite integral. So let me demonstrate through an example how we'll build up a similar idea. So suppose that a chemical spilled onto the surface of the ocean. We called the point where it spills the origin 0, 0. And this function here will give the concentration of the chemical at some point in time. So we're measuring here in kilograms per square kilometer. So if we wanted to estimate the total amount, that is the total number of kilograms of the chemical that were spilled, how would we do that? Well, let's say we had some region. Let's go from -3 to 3 in both the x and the y directions. So we've got some square around the origin. So this would be 36 square kilometers. The first thing we'll do is we'll divide our region into subintervals or subregions. So in this picture, I'll use n equals 4 divisions in each direction. And then in each of those regions, remember this is the domain of the function, in each of those regions we'll pick a sample point. We'll find some index to label them. Here I'll use jk to be the box in the jth column, sorry, the jth row and the kth column, measuring from the bottom left. And then at each of those sample points, we could take a concentration and assume that that's a constant concentration for that whole square or that rectangle. And then putting it together, in that square, the total amount of the chemical would be estimated as the concentration times the size of the rectangle. The concentration is measured in kilograms per square kilometer, the size of the rectangle, the area of the rectangle is measured in square kilometers, so we multiply those, the units check out. And then if we wanted the total amount of the chemical over the whole region, the whole 36 square kilometer region, we would just add up our estimates for each of the squares, and that would give an estimate for the whole region. So let's take a look at CoCalc and see what we would get. So here I have that concentration function plugged into Sage. And this command here is asking for a table of values. So basically showing us if we split up our region that goes from -3 to 3 in both the x and the y directions, what we would read at those 4 sample points in each row and in each column. That is, this 6.6 is the kilograms per square kilometer that we would find in that particular square of our 4x4 subdivision. And now if we multiply each of those samples by the size of the rectangle, that is the area of each of its subdivision rectangles, we get a total answer of 87.6 kilograms of the chemical. If we bump up n, we'll get more squares in each direction. Now this is still going from -3 to 3 in both directions. We're just slicing it up more finely. We can ask again for some of that. It's not too far off. We could ask for lots of them. Oh, this is going to take a little while on my computer. There we go. So again, still going from -3 to 3. Let's see how long this takes. Ah, that was fast. And so with 100 squares in each direction, we see this sum at 85.79 kilograms. And so to get a better and better estimate, we would take more and more samples. Remember, this is predicated on the idea that the sample we take, we're sort of assuming that it's constant over the whole square, which is not a good assumption if we have a big subdivision square, but it's not a bad assumption if our square is very, very small. Now, if we wanted a better estimate, as we saw, we need more rectangles. Or said another way, we want the size of each of our sub-rectangles to go to 0. And then to find the total estimate, we'd add up the estimates from all those small rectangles. And we'll use that idea to write down our definition of a double integral or region R for a function f of xy. We'll say that it's the limit as delta a, the size of those rectangles, goes to 0 of this sum, adding up all the sample points times the area of the rectangle. So this is basically our 2D version of a Riemann sum. And then the interpretation we're building here is kind of like that accumulation theorem, the fundamental theorem of calculus, saying that if we were to integrate a density over a region, the output should be a mass or a total amount. So in the next video, we'll see how we can think about these ideas graphically.